Perfect. Hello, everyone. We are live with the workshop, The Magic of TEs. We give everyone some minutes to join live on YouTube, LinkedIn, Phala's Twitter account. I think Secret's accounts are also streaming the event. Feel free to write in the chat where you're joining from and enjoy the music in the meanwhile. Perfect. Everyone from YouTube who's joining us, hopefully you can hear us as well. I see Patrick here. Hello. Great. Then I would say we kick it off because this session is recorded. I see people are joining on the live streams. Again, this session is streamed on Twitter, YouTube, and LinkedIn. This will be recorded, so feel free to also watch the recording afterwards to get back to this amazing content here today. A warm welcome from my side. I'm Zoe, VP of Growth at Phala, and the host of this session today. Today, we are talking about the magic of TEs, Trusted Execution Environments, a very hot topic. And I'm joined by amazing speakers here on stage. We are co-hosting the session co-hosting the session with our partners from Secret Network. We have Lisa and Alex here. Hello, guys.
Hello. Thanks for having us.
Yeah, thanks for having us. And very excited about the magic of TEs. They truly are a magical thing in the world of technology where we can enable so much with TEs. So I think we're starting this series and we really appreciate your bringing us on board. Secret Network has been, we've been working on TEs on mainnet since 2020, so quite some time. Definitely have a long history in this space. And it's funny because back when we started working on them, we were having the conversation, these are the future. This is what needs to happen for the future of confidential blockchain. And the conversation then was, no, we don't need that. Who needs that? Blockchain is anonymous and we don't need this stuff. And now it's a totally different conversation. So excited to be where we are today. Excited to be working with Phala, where we have several initiatives together, and I think we're moving the industry forward. Today, we're going to hear from Alex Zadelson about what Secret is doing with TEs, and yeah, just super excited to hear the content of this session.
Amazing. Thank you so much, Lisa. Thank you for having us. As you mentioned, Secret also an OG in TE cloud computing. So great to have you. We also have Dr. Shelvin here, who is lead researcher of Phala Network and the head of product. Hi, Shelvin, joining in very late from China today. Thank you for joining us.
Yeah. Also, it's a great honor to me to talk with so many professional guys here in this field. And yeah, I think just as Secret has shared, I think now there is some emerging use case for TE in the field. Actually, it's a kind of different from the previous private smart contract we have imagined, but it seems the TE is becoming like the cornerstone that back to the whole. I think it's very promising. It will be the cornerstone to back the whole blockchain world, and also even it's extended to more other fields like the AI model training field. So yeah, let's see how things will become. Yeah.
Thank you so much. Big promoter of trusted execution environments. We will hear also how Phala is integrating TEs into its architecture and combining it with blockchain technology. And we also have Andrew Miller here. Secret today without the camera, but maybe we will see him later on. Andrew, a researcher of Flashbots, also professor of cryptography, very, very big person in the crypto space. Very glad to have you here, Andrew.
Hey, Zoe. Hey, everyone. Looking forward to it.
Perfect. If maybe some of you guys have joined us 1.5 weeks ago with our first Twitter space. Just to set the stage here again, Phala, and in cooperation with a lot of partners, as I just mentioned, is hosting a 60 Days of TEEs, Trusted Execution Environments campaign. This campaign is an educational campaign to educate about this technology of trusted execution environments and how it can really enhance the Web3 space. Trusted execution environments are around for a long time, I think around 2013, but only taking off now or getting a lot of recognition how to combine it with blockchain technology. And Phala took the initiative and reached out to a lot of its partners also in the Web3 space to say that also build with trusted execution environments to say, hey, we need to use this opportunity and educate and really make sure why this technology is important and how it can be used also for the developers and what kind of use cases it can enhance. So just for the audience, thank you for joining here today. I will share the link later on about the recap of our first Twitter space where we discussed also what the hell is actually trusted execution environments. And today we have the second session, which is an online workshop where we go into the presentations of Phala Network, Secret Network, and Flashbots, how trusted execution environments are integrated in with or combined with blockchain technology as of today. End of this week, we also host our second Twitter space where we talk about use cases on trusted execution environments. So please watch out for the announcement there where we talk more about the real-world use cases. And there are more events and activities coming. We also have a quest challenge online that I will share later on where you can learn or also enhance your TE education and knowledge. Perfect. Then I would kickstart it. And before we also learn how different projects integrate TEs, we need a little recap of what trusted execution environments actually are. And therefore, Andrew will start with a 50-minute presentation about trusted execution environments basics. Over to you, Andrew.
Okay, outstanding. Let me get my screen share set up. We can go. Let me know it looks good, okay?
Yes,
Good?
I'm adding you now,
Okay.
And your slides are live.
Perfect. Okay, so I'm going to try to, thanks for letting me do this intro talk on this. So I'm going to try to do a couple of things. I'm going to talk about, my shortest concept intro lecture on what trusted hardwares are used for. I want to go into just one motivating application. That's a trusted setup cryptography application, but I think we can understand what it uses trusted hardware for really well. And I want to try to give my shortest possible live demo that I think demystifies a bit of what it's like to be a developer using this technology. So let me go through the concept of TEs, especially the way we use them in Web3. There's really, there's many kinds of TEs. They show up lots of places, but there's two main features we need from them, and they're isolated execution and remote attestation. And you should think of these as something that's provided by many of the server processors or business PCs like Xeons and AMD. Lots of different hardware providers provide CPUs that have these features. The isolated execution modes means that when you run something in the TE mode, not even the root owner of the machine is able to tamper with it or look inside the private data that it's computing on while it's running. So even the operator or the owner of the account can't peek through the isolated execution in this mode. The other cool feature that they have is remote attestation. So this basically means that there is the manufacturer of the trusted hardware. So Intel, in the SGX example I'll stick to, right? They have some well-known public key. And each one of the hardware chips that leaves them has some secret information in it that essentially enables it to sign certificates and signed messages with a private key that's associated all the way back up to the public key associated with Intel. And so this provides this remote attestation feature because you can check this chain of signatures and know that you're interacting with a real piece of trusted hardware. And the certificate that these generate also contains the program that's being run. And so what this all goes together and why this is useful at a high concept is that it's good for disintermediating app developers, because you don't have to take the app developer's word for things. You can say, grab the source code that app developers are saying is published, as a user or relying party or an auditor, can reproduce this compilation yourself and check that the software that you're expecting and have audited matches the software that's described in the certificate that's generated from the trusted hardware, and that you can check the chain of certificates is rooted all the way in the trusted manufacturer. And so if you know that you are interacting with a piece of code that you expect to and that's been audited, and it's with an authentic trusted hardware, then you're justified in choosing to trust your sensitive data to it. You know that it'll only be operated on by the software that's described. So I wanted to promise giving one really concrete example and then a live demo. So the concrete example that I want to give that ties this isolated execution and remote attestation together is the idea of generating a public RSA number. Now maybe this is technical, but this is intro cryptography. Outside the context of trusted hardware, this is a thing you may learn in other cryptography is a useful thing to do. I'll show you in this depiction what we want. This is a process for generating a useful number that you use in different cryptography schemes. And it involves generating a prime number P, generating a prime number Q, multiplying them together, and forgetting about P and forgetting about Q. Like you want to keep this product, P times Q, around. That's a useful parameter for your trusted setup. But these P and Q are called toxic waste because you're supposed to throw them away. They're supposed to be forgotten. And the security of things building on this relies on no one knowing that P and Q. So this problem, sometimes called a trusted setup, maybe you know from these KZG ceremonies and other blockchains that trying to do a good job of essentially this is something that people put a lot of effort into doing in distributed ways. We can do it with this trusted hardware way by running a program to do this trusted setup inside the trusted execution environment. And so I can give you this example of what this looks like in the Grameen framework. So this is like a Python script that just summarizes our application goals. Generate a prime number P, generate a prime number Q. We want to output that product and throw away the two things that we used as inputs. And so I'll just quickly give you the tour of this minimal demo, and then I'll run it on SGX and then on my laptop from the verifier's perspective. So this is my simplest possible demo. So it contains this Python script that generates the random prime numbers and multiplies them like I described. It also does the remote attestation step, which I'll come back to in just a moment. It involves writing to these Grameen framework files, but I'll come back to that in a moment. The other things that are part of the Grameen framework here is a description of how to collect up into the build, into the thing that's hashed as part of the remote attestation, all of the system files that are used and all of the Python dependencies. When I'm able to run this, I run this from a Docker file, which uses still part of the Grameen framework, a published Docker image, which essentially I will be running the manifest generator, which collects all of the system files that are relevant for running Python. It will collect those and the Python interpreter itself and the Python script that I'm including. It'll bundle all of this together into one program, and that's what's going to run in the trusted execution environment. So I'll show you what this looks like. I'm logged into my SGX machine. I'm able to follow these build steps, and when I run them, the default thing that I see is this measurement. So this is the measurement reference. It's called MR Enclave, and this is clearly a hash. And this is a hash of my entire application, including all of the Python binaries and system libraries needed to run it. And the next thing that I can do, you can tell that this is an SGX machine. I run one of the little debug tools to show I'm running a machine that's capable of this trusted hardware environment. When I actually go and run the enclave, what it will do is generate the output of that program. So this is the RSA number that it generated. This is the hash of that number. And what's down here is called the quote. So this is that remote attestation certificate that's generated that can only be generated from an SGX, a trusted execution machine. What I can do with this quote and the significance of it is now if I go to, this is now just my laptop, not even SGX capable machine. I don't have SGX available on this, but I can still reproduce the build process as though I were the verifier or the auditor trying to understand, trying to see whether or not I believe that this trusted, setup was done correctly. So I can do the same steps that involve checking the hash of the entire binary. You can see this hash matches exactly the hash that was built on my SGX machine. And I can also, as the auditor, simulate and run, whatever I would need to in this machine. I'm just running it locally. If I run that application here, I generate a random number, but it'll fail at the attestation because this is something that's only available on my trusted hardware machine, which this is not. This is, again, just my laptop. But what I can do is run the quote inspection tools. So here on my laptop, I just will use one tool that I like to use, this Grameen quote viewer. And if I run it on parsing the quote that's available, you can see some of the structure of this remote attestation. So really the key things are here. This is now the measurement of the enclave that comes in the signed package, right? And that hash matches the one that I was simulating and the one that I actually ran on my machine. And the report data here is something that's specified by the application. We looked at what this application did, and now this is finishing the explanation of what the attestation is. It has two steps to use the remote attestation. You set the application to find data. In this case, it was the hash of that number I'm claiming was generated from this Python script running in the isolated mode. And after setting that hash, that matches what I have, that's included what's in the quote. So looking at the structure of that quote, this report data contains the hash of this. This enclave measurement contains the program that I've reproduced the build of and can inspect how it generates numbers. And the last thing here is the signature. I'm not going to go into the details of how you verify all of this, but this is a signature that you can verify ultimately that's signed by Intel at the base of a certificate chain. If I put all of these together, that's my justification for having checked some evidence that, yeah, the RSA number whose hash is this, I can believe was generated in a real enclave and therefore, threw away the P and Q that it was supposed to. Okay, so that's the end of my demo content. I think I covered all of the extra notes that I really want to and probably want to save a bunch of time. I showed you that one quote viewer. I like to talk, as this is, a Web3 crowd, about the on-chain attestations, but maybe we'll save that for another time. There's a bunch of security caveats that are relevant as well. Maybe I will clean up the time here, and so only come to those if I want that. This is actually a photo. I'll just throw in one insight as the way of ending security. So this is the photo of that machine that I was logged into. It's an SGX, but it's one that I have physical possession of. And so, one security insight is that if there were anything that I could do with physical access to the machine, if all you knew was that you checked that quote, right, it could be coming from this machine in my basement laboratory where I'd be able to amplify any side channels that I could. Anyway, this is a nuanced topic. We'll come back to that if there's questions maybe, but let me wrap up my portion of discussion there.
Yeah. Thank you, Andrew. I think it would be great to dive a bit deeper into the security caveats, the slide that you had. I think it's good to take the time for this because it's a basics workshop and a lot of people really want to learn about it. So please feel free to get back to the slides. I will add it 1 second. That we have the baseline correct. Perfect. Yeah.
Okay, yeah, it's just a couple of points because this is about the magic of TEs, and that is really the fun thing, is to see what kinds of things are implied by this really interesting new powerful tech. It definitely comes with caveats. Some of these are just things to be aware of, like risk awareness. Other things are things that I think create tech debt that we need to work on quite hard as protocol designers and devs and software engineers. So I mean, starting from the top, the trickiest thing with relying on these trusted hardware from vendors like Intel and AMDs, you really do have to trust them. The most performant and flexible ones like SGX, and it's true of others as well. I'm mostly just familiar with those, but they've all had a bunch of vulnerabilities that make you question, using it for the most extreme or sensitive or high value cases. There's also some sense in which it's very centralized in its trust. I gave in my example that there's public keys and the private key is held by each device, and the public key is somehow known by Intel. You really have to trust them to run this ongoing service. You can't really tell whether or not they've injected some spyware enclaves that are authorized as well. There's no particular reason to distrust them, other there's been this history of vulnerabilities to have to work around, and this trust model involves quite a lot of centralized trust on the manufacturer. I did my little slide there about, physical attacks are something to consider. Some of the vulnerabilities are only possible with physical attacks. Others are vulnerabilities that can be exploited even with just software access. The ones that can be exploited by software access, even more so, you have to think of software defenses to try to mitigate them. And the last thing is a catch-all, so I won't go into examples for that here, but it's actually really challenging. It seems like this trusted hardware is magic. It is really powerful, but it's not all powerful. And most of the interesting applications, we'll hear more about those in this hour, involve the use of blockchains working together with the trusted hardware. But that's very difficult to do right. It's not any easier than smart contracts and blockchains. Those are notoriously difficult to get right as well. So hopefully security continues to come back as a theme of educating in this campaign.
Perfect.
Okay.
Yeah. Thank you very much. This was a quick intro, definitely a deep dive, since we also saw the remote attestation code. Thank you very much. For anyone from the audience, please feel free to add questions. Also, if they're very basic questions, we can recap them later on also as discussion between the speakers. But since we only blocked 1 hour today, I would directly hand over to Dr. Shelvin from Phala, who will now build on top of the basics that Andrew just explained, to explain or to showcase how Phala Network implements trusted execution environments in its architecture. And Shelvin, feel free to also follow up on any of the details that Andrew explained, and we will hand over to you.
Okay. Yeah. So thanks Andrew for the sharing of all the basic information about TE. So here I'm introduce Phala Network. So it's actually a position as a extra security layer over TEs, because just as the security caveat has discussed. So actually I think the philosophy here about TE is that first there is no doubt that the TE is adds some extra security promise over the raw CPU. So it's security features, so it's far better than the raw CPU itself. But actually, we do not trust TE for no reasons. So because actually the fact is that there is some historical vulnerability reported for the TEs. So, but on the other hand, actually there is some I would say procedure you should follow. For example, there is some rules called responsible disclosure, because, for example, when you try to find some vulnerabilities and you try to write a paper on it, so before you really publish that, you need to first report that to the manufacturer. For example, we have to report that to the Intel first, and then we work with Intel to work on the patch, and only after that we ensure that all this patch has been sent out, we can publish the paper about it. So it's the responsible disclosure. So this means if we can follow the standard procedure to use these TEs, actually I think the security level of TEs can be improved better. So, and in my talk, actually I think I'm only here to answer one question here, is that what's the difference between using a TE from Phala Network or from Secret Network, and setting up a TE hardware myself and just to run it locally. So what's the benefits that our service can bring? So here I think the first okay, can you see the changes here? Oh, let me. Yeah. So if you just use a single native TE yourself, actually there can be some problem here. So I think the most of it is due to the internal limitation of TE itself. So first is that although TE provides the promise of confidentiality, so the privacy of your data, and also it provides the integrity of the program. Just as Andrew has just shown, you can see the hash of your program code and also the initial states of your program. So you can remotely verify that, okay, all of them are not modified by any third parties. But the problem here is that the TE itself didn't provide the service availability promise. This means, for example, the TE hardware itself can be broken. And also, like, you cannot prevent like these operators from like unplug your hardware. So this, if they do such kind of things happens, then like your service will down. And since your program is running inside TE, sometimes something worse can happen, because like the TE itself provides some secret keys to seal your data, to store and encrypt your data to the disk. And such keys from TE is highly coupled with the hardware. So this means, for example, if you try to move the encrypted like disk image to another TE hardware, it cannot be directly decrypted by the TE. So if your previous TE hardware is down and is broken, then this means your data can be frozen forever. So yeah, so this is the cost of the all the security promise from TE. So this is the first problem. And the second problem is the vulnerabilities. So like all these vulnerabilities can mitigate all these confidentiality and integrity promise from TE. So this can cause some potential data leakage. So from if you are running something inside TE. So both of these, I think such problems cannot be simply ignored. So we have to treat them with carefully. So this will be the problem if you try to run some TE yourself. So instead, I think the Phala here is that we wrap it as a service. So this means first we have a lot of TE nodes for you to use. So like if some of the nodes are down, we can very easily find some replacement for you. And on the other hand, we have some extra security like layer here to ensure that your program, for example, if one TE is down, your program can still be safely moved to another TE instance and resume to execute. I think this is very important for those projects who really serve their customers, because the customer don't want their data to get frozen forever. So here, Phala now is one of the biggest TE network in the world. So now we have over 31K online workers, and this is still increasing. And also, like all of these workers, they need to be staked. So like these hardware operators, they need to stake Phala tokens to these workers. So these stakings are served as the security deposits, and also we have the tokenomics to encourage them to well behave, to provide high quality services. And now we have a live map of all the workers. So you can see that, so it's a P2P decentralized networks all around the world, and every node in it like come from our community, and all of these nodes, they are TE hardwares. So you can see it's from like Europe, China, Japan, also like North America here. So actually this is not a complete map, because we cannot enforce our every nodes here to report their true IP address, but I think this already shows that actually this is quite a decentralized network all over the world. Yeah, and yeah, so this is the extra security feature we majorly like provide here, is that so first, all these contracts in our platform is called AI agent contract. So every agent contract is running inside TE, and your contract is safe even if some of these TE workers are down. So if some TE workers are down, so the network will automatically move your agent contract to other TE worker that's still alive, so your service to the customers can still alive. Yeah, I will give a high-level introduction of how these things are happening. So first, like actually, if we want to use TE to run some program, so with privacy, So the very trivial solution here is that, so for example, we can generate some secret key directly inside TE. So it's generated and used only inside TE. So unless this TE is fully compromised, so the outside world cannot see the secret key, so your program state is safe here. So, but this also means that like only this TE is able to decrypt the states of your program and get it running. So this is how it works. So the TE generates the keys, and it's used one key for all the programs that's deployed to this hardware. And for every time it's tried to run in this program, so it's used its secret key to decrypt the states and do some calculation, update the states, and it's encrypt the states back and store it back to the disk. So this is how the whole process happens. Yeah, but there can be some problem here for this trivial solution. So the first problem is that, for example, if the T is down, then this can also means you lose the secret key forever. So then all these encrypted states can never be decrypted anymore. So since we cannot restore the original states of the program, so this means your program is also frozen, is also dead here. So this is the lesson one we can learn from this model, is that so do not totally delegate the key generation to one T, because if that T is down, then this means all these data encrypted by these keys will be frozen forever. Okay, so the second problem here is that since we use one secret keys to encrypt the data of all these programs, this means actually this brings a very high risk here. So for example, if this secret key is leaked, so for example, this T hardware is like compromised, then this means the attackers can use these keys to decrypt the states of all these programs. So this increased the consequences that an attacker can create by like compromise a single node. So this is the second lesson we can learn here, is that do not use the same key for all the programs here, because like in the previous sgx.fail. The website, actually Andrew team do the work. So if like they compromise the keys, one key from one node, that this means all the secrets are leaked in this case. Yeah. But for our side, actually, we have some insight in this problem. Is that I think the most important things here is that we should decouple the program states from TE instance, so this program can be freely moved between different TE instances. So and to achieve this, there is two concrete problems to solve. So the first is the key management. So how we generate this secret key and how we share it across different TE instances. And I think the second problem here, I will not discuss it in this case, because actually in smart contract scenario, so this is not a big problem, because all the smart contract states are naturally stored on the blockchain. So it's naturally shared across all the nodes. But the state storage problem, so when we encrypt these states, where should we store them, and how can we ensure that all these TE instances can get access to these encrypted data with correct access control? So this will be a problem for more general purpose real-world programs. For example, like the AI model training and AI model inference problem. Yeah. So yeah, so let's focus on the key management problem in this case. So the solution from the Phala point, and actually I think this is not created by Phala. So this is first proposed in a paper called Accident, and this is adopted also by the Oasis network. Is that it's introduced a standalone key management service, so to do all the key generation and key distribution work. So instead of ask every TE worker to generate the key themselves. Yeah. So here, let's see like what's the things will happen like under this model. So first, like we can have a standalone key management services. So in Phala case, we also use TE to consist these services. So like we have some special node called gatekeepers. So they are the members of the key management service, and they are the root of trust of all the network. So like so we can see here, like here we can adopt a simple duplication model here, like the same key is shared across all the TE gatekeepers, and only if like the TE workers they are authorized, then like these keys will be shared to these workers for the real execution. So in this case, so even if like some TE workers are down, so like the KMS, since it knows all the keys, it can still find some replacement TE workers, and it share the keys to them so they can keep the execution continue. And in this case, since like the keys are duplicated across all the TE gatekeepers, so only if there is at least one alive TE workers, TE gatekeepers, then like the whole network is safe. So it can still distribute these keys to the workers as needed. Okay, so about some TE, so what's the difference between the gatekeepers and the normal like TE workers? So the first is that like since we follow the on-chain governance, so all these gatekeepers they need to be chosen by the on-chain council. So instead of like some centralized selection of these workers to be the gatekeepers. And second, I think this is partially covered in the previous talk, is that actually in every remote attestation report you get, there is one field so called like the quota status. So in the Intel case, there is different levels of this field. For example, in this example, this field, the value is called configuration needed. So this means you should like try to apply some patch of your firmware, and like to change the configuration of your like BIOS or motherboard, or even like update the microcode for the CPUs to apply the patch for the vulnerabilities of your TE hardware. But in this case, like for the gatekeepers, actually we require all the gatekeepers to be the first level, tier 1. So the value is okay, and here the okay means this hardware is not affected by all these known vulnerabilities to the TE. So this means actually different TE hardwares also have different levels, and some we require those most secure TE workers to be the gatekeepers. So it has the lowest chance to leak these important keys. Okay, so then come to the second lesson, is that we should not use the same key for every like applications in the network. So so in our design, we generate unique keys for every contract running inside our network. So like the KMS itself, it's only take control of the root of keys, which is called the master keys. And here we rely on some cryptographic function called key derivation functions. So these functions can be used to generate keys based on the master keys. But actually, all these generated keys cannot be used to infer any information about the master keys. So this is the one direction generation of the keys. And we use these primitives to generate contract keys for every different contract. And also you can see like actually you are free to deploy the contract to different TE workers. For example, in this case, contract 1 and 2 are deployed to the first cluster of TE workers, and contract 3 is deployed to another cluster of workers. And here the deployment means that the KMS will distribute these contract keys to the corresponding workers for real execution. Yeah, so this is a very high-level overview of like how we do key management in Phala Network. But actually, there is some more features to come since we are like heading towards more complex use case. So I think there will be 4 things to come. So first is the TE GPU support, because like in last December, NVIDIA has released the first commercial available TE GPU H100 series, and I think many teams are doing the experiment on that, because this extends the TE support from CPU to GPU, and this will enable a lot of new use case. And second feature here is called global key rotation, because you can see in last model here, all these keys, they are static. So this means these keys are there forever. So actually this is of very high risk, because you don't know when like the attackers can compromise like one of these nodes and the extracted key. So one mitigation to that is to enable the key rotation. This means we can change all these keys regularly at certain interval. For example, we can rotate the key like of all the network like every 30 minutes. So this will increase the security level of the whole network, because this means the attackers, they need to extract these keys like within 30 minutes. And after they have done that, actually, they can only use it for 30 minutes. But because after 30 minutes, all these keys will be changed. Yeah. So this will limit the attack interface of all the attackers. Yeah. So the third part is to how to enhance the KMS. So in our examples, we just used the most simple mode here, that the same key is shared across all these TE gatekeepers. But actually, the KMS itself didn't necessarily need to be like using TE. For example, it can be a purely like cryptographic KMS here. For example, you can just use all these MPC like algorithm. And since the KMS itself, the functionality of KMS itself is quite simple, because it just need to manage these keys. So actually, like it can help mitigate many problems from the MPC. For example, MPC is kind of slow when you try to run in some complex program here, but it's okay to use it to just like run the key management functionality here. So yeah, and the last case here is the complex program support beyond smart contract, because I said that like the smart contract, it didn't need to handle the state storage problem here, because it's naturally solved in the blockchain use case. But in real world, the thing is different, so we need to handle this problem. Yeah. Yeah, this will be the general contents of my talk today. Thank you.
Thank you very much, Dr. Shelven. This was a great overview. Still very high level, but I think a lot of educational content for everyone that learns about Phala Network the first time. Also laying out the unique approach of Phala, right? I think the two things, Dr. Shelven, that the audience should take away is like really the key hierarchy and the key rotation. That what makes Phala's architecture on a high level very unique. And of course, all the details that Dr. Shelven just explained. Just on the last slide, MPC was mentioned for everyone that's also new to these short terms. It's called multi-party computation. So trusted execution environments can be also used to offload some of this compute for multi-party computation, as Dr. Shelven mentioned. We will talk about some other technologies or combination of technologies also further down the line in our TE campaign, how to combine TEs with ZK, MPC, and so on. But more to this later on. Thank you so much, Shelven. If there are any questions from the audience, please feel free to put them into the chat, and we can come back to them later on after our last presentation from Secret Network. And we also shared the docs to Phala, or the link to Phala Network's docs, so feel free to check out more information there. Perfect. Then I would hand over to Alex, CEO of Secret Network, also building with trusted execution environments for a very long time. And I will get your slides on stage, Alex. Over to you.
Hey, thanks everyone. So my talk is actually much less technical and more like generally educational. And like large parts of it were actually covered by both speakers before. I wanted to talk, in the previous spaces we talked about TEs and how it's like a magical black box. So I wanted to focus on this concept of attestation. And although it has been covered in a way, I think for the benefit of the more general audience, it's important to go through that and make it clear like what it is and how it works and why it is important. And I'll touch upon how Secret uses TEs a little bit just in the end. Okay, so let's go. As we discussed, I need to go here. So as we discussed right before, so as I like to put it, TE is like a magical black box, right? That has its own public-private key pair and that has its own data and nobody can get into it. But how can we actually trust it and know who we're talking to? So that's exactly where the concept of attestation comes in, right? Because when I send data to this black box, I need to be sure what it is and that it's genuine and that it's real. So that process is called attestation, right? And the way it actually basically works is that this enclave, this black box, it creates some sort of a report. And then there is an attestation service that actually validates this report and tells us, okay, is it good? Well, first of all, is it the right hardware? And also, what is the software that's running inside this black box? And then as the user, I can really decide whether I want to trust it or not, right? So this is the main fields in the attestation reports. Again, Andrew covered them a little bit, but I'll go through them again. So what we can see here is what kind of a CPU we're talking about, right? What kind of security version we're talking about, right? Meaning whether all the patches are in there. It also gives an information about the hash of the software that is loaded into the enclave, right? And I, as a user, I can verify it, right? Because it's one thing knowing that I'm talking to this secure TE, but maybe the software there is has been compromised, right? Or maybe it's not exactly the software that I'm expecting. So this MR enclave field actually allows me to know which software is running inside. And MR signer is actually the key of the entity that signed the software, right? So this is the basic information I can get from the TE in the attestation report. There are some custom fields that the software can fill in. Like report data, and we actually at Secret, we use it in this node attestation procedure that we'll talk about. So specifically, we at Secret, we're working with Intel SGX, and Intel SGX currently supports two attestation types. Okay, the old one and the new one. So I want to talk about them a little bit here. So the first one, the older one, is called EPID, Enhanced Privacy ID. It's actually the way it works. Actually, that you get the report from the TE, and then essentially it's sent over to a centralized Intel server, from where the user actually gets a response saying kind of yes or no. Okay, and the response actually says whether the hardware is genuine, whether it's good enough, and whether you should work with it or should send your data to it. The disadvantage is that of course it's fully centralized, right? So there is a single point of failure there, and probably Intel realized that this scheme is not the best, and it's actually going through end of life in 2025. Although up to date, from what I found, it issued over 4 billion different keys. Now, the newer scheme, which is called DCAP, and to which we recently upgraded our network, data center attestation primitives. It's available on newer generations of processors, like third, fourth, and fifth, on which, by the way, the older one is not even available. So before Secret upgraded to decap, our nodes could not run on those newer generation processors, so now they can. And in this scheme, the validation itself is actually delegated to a third party. So Intel just shares a bunch of certificates that they gave out to different vendors, and then when the report is received, every company can actually validate it on its own and even set its own rules, right? So we can decide to, like, which level of software patches is required for the machine to be eligible to join the network, and whether it is acceptable. So there is much more control given to the developer of the product and taken away from Intel. So generally, this scheme is indeed much better and newer. So we're implementing it right now. So I mean, it's already implemented in Secret Network, and I guess in a lot of other projects that are working with TEs, just because I think in April 2025, EPID will not be working anymore. So here are some schematics of how those systems work. There is like a similar flow that you're getting a quote and then you're testing it, but decap is a little more involved with the internal attestation service running here. I don't want to go into too much detail here. The basics is, again, you get some report from the TE, and then it is validated. And in the case of EPID, it's validated directly by Intel in a more opaque way. And in decap, it's validated by a separate service that every developer can run on their own. So coming back to Secret, right? So the goal was to speak about how we're using TEs, right? So Secret is a Cosmos blockchain, essentially, where all the smart contract execution runs inside TEs. Okay, so we have taken the Cosmos execution module and we have put it, this Cosmos WASM runtime, we've put it inside TEs. And so whenever users send transactions, the transaction data is all encrypted and can only be read by the TE. So only the contracts are all executed in the TEs, providing a full privacy to the user, right? So, and the contracts include basic things like tokens, right? In Secret, you can create a token contract, which is very similar to ERC20. And all the balances are confidential, right? DeFi contracts where you can swap things and nobody can front run you just because the amount that is being swapped cannot be observed. Voting contracts, any other contracts, I guess it's a topic for another talk on what are the use cases, right? So as we know, TEs may be vulnerable to attacks. Right, and this also happened in the past, right? When information was extracted by TEs. So in Secret, TEs provide the privacy, but the data integrity is taken care of by the consensus, right? So even if TEs are breached, there is no risk of funds getting stolen, right? And it's an important property. So it's like a double check system in a way. And here's how attestation works at Secret, right? So when the network starts, the Bootstrap node actually generates what we call the master key, right? So that's the master key that encrypts all the network state, and that actually and that all the validators in the network must have in order to execute the smart contracts, right? Because only this way we can reach consensus and get the same results. So when a new node actually joins the network, they go through all the attestation process, and then they post the attestation report on chain. And as part of the attestation report, they post also their public key that is then used by other nodes, by the Bootstrap nodes, to initiate like a DeFi Helmet exchange and share the master key with the new nodes. And that way, every new node that joins the network can verify that it's running the right hardware and also the right software, because we check the MR enclave field to make sure that the node runs exactly the same software as all the others are. And only after this attestation is this new node accepted into the network and receives the master key. Okay, so that is actually the contents of my talk. Again, it's lighter and less technical, but I hope it was useful for people to understand the importance of this concept of attestation and how without it, this whole TE environment cannot really be of use. It's an integral and super important part.
Perfect. Thank you very much, Alex. This was a great roundup to the previous presentations. Very good overview. Also, if it's not too in-depth, we will continue the workshop session. So there's more opportunity to go into the demo code also on Secret Network.
Sure.
Great. We will wrap it up here, but the audience has some more minutes to ask specific questions, if there are any. I have a question to the panelists here. We saw already, thank you again to all of you, to give a mix of like how really trusted execution environments work on the code level. From Andrew, we have seen like how Phala Network specifically integrates trusted execution environments with the key hierarchy and key rotation. And Alex summarized this beautifully on a high level, how trusted execution environments work from a non-so-technical level, as well as how Secret implements TEs. Maybe for everyone that joined also a bit later on, what would you guys suggest if we have a lot of builders here also today that, or also non-builders that want to educate themselves further, where to start if they want just to educate themselves, and also if they want to kickstart on building? Dr. Shelvin, what kind of resources can you give the audience?
Yeah. So yeah, I think first, I just recommend everyone to read the documents from like Secret Network and also from Phala, and also to join the forum of Flashbots to learn more details. And also, since I think all of us just provide some well-wrapped service, so this means actually it's help abstract out many underlying details for you to get started. And second, just in Andrew's demo, he used a project called Grameen. Let me share the link. Yeah. So Grameen is a very good, I would say it's also a very good abstraction layer of the underlying TEs. So I think the good part for it is that if you are using the Grameen, actually you can just, you are just feeling like you are not programming on the TE hardware, you are just running on a normal like in Linux server. So I think this can help like reduce many problems, for example, to at your first step into the TE world. And also, I think don't need to be afraid of the TE things, because like every TE environment, it provides the software emulation part. This means even if your CPU is quite old and it didn't support TE, you can still kickstart the programming and the debugging inside your own hardware. So yeah, I think just try to I think that just try to get the hands dirty and start programming.
Perfect. Alex, Andrew, any information to add?
Well, I think San already shared our docs. So I mean, people who want to build should just look at our docs. We're using Rust for smart contracts. So people familiar with this language, it should be pretty easy to start. And I hope we continue those workshops and get into more details on like deeper technical issues and examples.
Thank you so much, Alex. Andrew, I already shared the wiki, the TE wikis from Flashbots, a very, very valuable site. Is there anything else that you would like to share or give as information to the audience?
No, I loved it. That was what I would have wanted to share. Thanks.
Perfect. All right. We would wrap it up then here. And thank you everyone for joining today. This was our first online workshop, the basics of TE, with a lot of deep technical content, but also high-level educational explanations. I think it was a great mix from Phala Network, Secret Network, as well as Flashbots. And we will continue these educational sessions. Again, this is a workshop as part of the 60 Days of TE campaign hosted by Phala in cooperation with a lot of partners. We will continue also the cooperations, as mentioned in the chat here. Someone wants to see more use cases between these protocols. This will also happen. So please join us for our next Twitter space the end of this week, where we will discuss the real-world use cases of TEs. And then we will also continue with technical workshops where you can learn more how to build on different TE infrastructures. Thank you very much and see you all very soon.
Thank you very